Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. We are going to do trapping rainwater problem today, and if you want to see that what are the list of companies that have asked this question, that comes later in the video, so you can directly check it from there. Let's understand the problem statement. We are given an array called n, where all the integers are non-negative, and any single integer represents actually the height at that particular position inside the array. We are given that the width at any two positions is actually 1, so we can consider that, and we need to see that how much water can we trap when it rains. We know that it's going to rain a decent amount, so we all the cells that could trap water would trap water, and our aim is to see that what is the maximum unit of water we are going to store. So let's try to understand this with an example. Over here we are given an elevation graph, and all of those values are represented as bars inside the given graph. And we notice that because there are some height differences, due to the height difference there exists an empty space inside this given input, and because that empty space exists, rainwater can actually fall in and be stored on those particular positions. So if we see over here, like this first position is actually 0, and suppose the rain falls, can any water be stored over here? Well, it cannot be stored, because in order for water to be stored, we need a vessel like this or something like this, where at least water can be stored. Like over here, if we see, water can be stored for all of these positions, because all these three edges were covered with some sort of solid material. Same goes over here. Like over here, we can only fill water up until this point, because on the left side the edge is only up until this point, not more than that. Like though on the right side the edge is actually higher, but if we try to fill in more water, or if rain falls and more water falls on top of it, all the water is gonna spill out, and no amount of water is gonna be stored. So that is one key important part, is to understand that how water is stored. And second is that we need to iterate over this given input height, and at every single position we are going to basically calculate that how much water can be stored due to this height difference. So if we see in this example, at this first position no water can be stored, so like there is no water pointed with over here. Like this is a bar by itself, and in this particular bar, this is the boundary, that is a solid surface that cannot store any water, and we cannot store any water on top of this one, because all the water that gets stored on top of this one will also spill out, because on the left side the boundary is actually non-existent. Now if we look at this third position over here, actually because of there exists a height difference between these two positions, we have a scenario something that looks like this, where water, when the rain falls, on the left side we have a bar of height 1, which is represented over here, and on the right side we have a bar of height 2, which means that we are creating some sort of value over here, where on the left, at this particular position on the left side, the bar is actually of one size, so this is of one size, and this is bar of two size, so this is actually two size, which means that there exists an empty vacuum where water can fall in and water can be stored. So this becomes our point, and we can check that over here we can store 1 unit of water. Now the question comes that why can we only store 1 unit of water? Why cannot we store more than 1 unit of water? The formula is actually quite simple. Like at this particular position, we see that on the left side there exists some height, on the right side there exists some height. So suppose this one is left height, this one is right height. There are two heights that exist at any moment, and this by itself can have some height, as mentioned in this input, that there can be some height that can be located at this position. And suppose this position is actually the height we are currently at, so we just name it as height. Okay, now how can we determine that in this scenario? In this scenario, if we see does all these values, so left height is actually 1, okay, right height is actually 2, and the height we are currently at, which is this position, is actually 0. And over here we were able to store only 1 unit of water. So why we were only able to store 1 unit of water? Basically we were following this condition that first of all we need to check that what are the bar height difference between on the at any given position on the left hand side and at the right hand side, and we need to take the minimum out of both of them, because over here, though on this right hand side the bar is actually of height 2 units, because on the left hand side the bar is only of at a height 1 unit, we cannot store water more than this height because the water is gonna spill out. Now that is one condition. Now second condition is, in this case we got lucky that over here there is no height at all, so that's why we were able to store 1 unit of water over here. So basically we can say that at any given moment the amount of water we can store in 1 unit is actually following this formula, that the minimum of whatever the right height is, whatever the left height is, so whatever the lower value of both of these minus the height we are currently at. And if this is greater than 0, then only we can say that we can store some water at any given position. Like let's say for an example that why at this first position we are not able to fill out any water. And if we see both the values, so on the left at this particular position I'm referring that on the left side the left height we had was actually 0, the height at current position was also 0, and the right height was actually 1. So if we apply this formula, we can clearly see that on the amount of water we can try to fill in this space is actually going to be minimum of these two. So minimum of left height and right height is actually 0 minus the height we are currently at. So current height is also 0, which means that we cannot store any water, or we can store 0 units of water at this particular position or at this first position, because there exists height difference. And same formula can be applied for all these places to calculate that what is the amount of water we can store. Like if we see over here, the bar height is actually 2. Now for this particular position, if we want to check that what is the amount of water can be stored, we know that over here we can store 1 unit of water. And why we are storing 1 unit of water is because if we see the left height over here, that is 2. Now on the right side, the right height, there is no right height over here. There is no right height over here which is greater than this one. Like this, there is some right height over here, but that is less than this height. So there is no point in us to treat it as valley up until this point. But over here we know that the height is actually greater than whatever height we currently had over here. So this right height is actually 3. So we are going to check, so we are going to apply the same formula. So we are going to check the minimum out of 1 and 3, one minimum out of 2 and 3. So this is left height, this is right height, and we are going to minus whatever the height we are currently at. So current height is actually 1. And if we apply this formula, we get 2 minus 1, so we get 1, which means that over here we can store 1 unit of water. Now let's try to understand this one with another example, and I'm spending a lot of time in this one because this is the actual crux of the entire example. So over here, if we want to calculate that how much amount of water we can store, we are again going to repeat the same process. So what is the left maximum height we can find for this particular unit? Like the left maximum height we can find is actually 2 units. So we can say the left height is 2. The right height is this one, so right height is 3, and minus whatever the height currently we have at this position. So this position we don't have any height, so which is 0. So if we apply the same formula, we can get 2 minus 0. So we can say that over here we can actually store 2 units of water, and which is what is presented over here. Like that's how we can store 1 unit of water over here, and that's how we can store 1 unit of water over here. So at any given position, for any particular element, we are only going to need 2 things, because height we are already given. So we remember that in this equation we are actually comparing 3 items: the right maximum height, left maximum height, and height we are currently at. So height we already know, and our aim is to find that how can we find this right maximum height at any given element, left maximum height at any given element, and then it would be piece of cake to for us to identify that how much water can be stored at any particular position. So we can have a brute force approach where at every single position we iterate over the entire left array and entire right array, and we find that what is the maximum left height we can find at any given position. We can also find what is the maximum right height we can find at any given position, and we already know that what is the height we are currently at. And once we have both of this information, we would calculate our result, and we would try to calculate our output. The thing is, this scenario is pretty darn bad, like at any single position. So even over here we will have to iterate over the entire left array and entire right array in order for us to calculate these two values. And yeah, this is brute force. So brute force is tend to be dumb, like we are not doing anything clever over here. So that's why we would end up with the time complexity of big O of n square, because at any single position we are going to iterate over the entire array to find these two values, left height and right height. Now can we do something better over here, and how can we find a better approach? Like so for the given input example, we can actually do something clever. What we can do is whatever the input we are given, we can actually iterate over it from the left side, and at every single position we can see that for any single element what is the leftmost value or left max value we can store. Again we are going to iterate over the given input example on the reverse order, and then we can find that at any single position what is the right max value we can find. And then it becomes pretty simple for us. We can just simply apply this formula on the entire input that were at any single position. So at any single position we only need to find the minimum value of right max and left max minus whatever the height we are currently at, and if this becomes greater than 0, then we will add it to our whatever the output we have, and this would be our answer. So let's iterate over first on the left max side on this given input. So on the first element the maximum left height can be 0. Over here it can be 1, again over here it can be 1. Now over here this value is 2, so left max height at this position would actually be 2. This would actually be 1, but thing is we have already find a greater value, so again we are going to keep it as 2. Again we are over here this one is 0, so again the left max height we can find is 2. Over here this one is 1, so again this would be 2. Now this is 3, which means that left max height we can find is actually 3. This is 2, so left max height we can find is actually 3. Again 3, again 3, and again 3. So this is how we can fill out this left max table. Same way we are going to fill out the right max table, but we are going to do it in the reverse order. So over here the right max edge is actually 1, and we are going to repeat the same process. Now we have both of these tables filled out, it becomes pretty easy for us to find the solution, and we can actually do it everything. Now this approach would work perfectly fine. The thing is, what is the issue with this approach? Like if we calculate the time and space complexity, the time complexity for this one is actually big O of n, because we are doing everything in just a single loop, and we are running this loop 3 times. Like first we are running this loop, so we are doing n work, again we are running this loop, so we are doing n work again, and then we are running the n work to find the output. But thing is still time complexity is going to be big O of n, and the space complexity for this one is actually going to be big O of n as well, because we are storing these two additional data structures. So this is much better improvement than our brute force approach, where in the brute force we are doing everything in big O of n square time. So we are gaining significant improvements over here. Now this question has been really popular with a lot of different companies, and if we just look at the number of companies that have asked this question, and if we just see the amount of frequency that they have been asking this question, I wouldn't be daring to skip this problem. Like even if you see up until 2 years, almost all the companies that are like one of the biggest companies in the world, they are continuously asking this problem. Just look at the numbers, like Amazon, Facebook, Goldman Sachs, Bloomberg, Microsoft, Google, Adobe, Uber, Apple, Tesla, Lyft, Expedia, Morgan Stanley, Swiggy, ByteDance, Databricks, Walmart, Flipkart, ServiceNow. These are the companies that pay you in gold bricks. And getting job or getting employed at any of these companies at least for 2 3 4 years is going to change your financial situation drastically. Like it's going to be 180-degree turn, and you only need to clear the technical interviews just once. Like after that you are sitting on top of gold. So if you are also dreaming to changing your life completely, like make sure to focus your utmost attention to this problem and try to solve it as many times as possible, because it has been asked in so many companies. So that tells you something. Okay, now for the optimal solution, we can actually observe something pretty interesting in this given left max and right max that we have calculated. If we notice in the given input, this is the biggest bar of height that is possible, and we know that at any moment, at any location, if we want to find the height, the equation is this one, that the minimum of whatever the left max and right max we have minus whatever the height at current position we have. This is the equation to find that how much amount of water we can trap at any given unit or any given elevation. Now the thing is, if we notice in these two values, left max and right max, we are actually finding something pretty interesting. And the interesting thing we are finding is that the tallest part that we have, it actually divides the given input in two parts. And it divides how? That if we observe the left max portion, the left max portion is always less than whatever the right max portion is up until this point number 7. Because notice all of these values, in all of these values the value of left max is actually less than whatever the value of right max is, and over here it's equal to right max because of this particular tallest bar that divides two arrays. And all on the right side, actually the R max is less than left max, and we can see those things over here, that over here these are all the values that are smaller than whatever the left max there is, because for these four values actually this particular, the tallest bar actually becomes the left max element. And using this we can actually use it to our advantage, because remember, at any moment if we want to find that what is the amount of rainwater we can pound, we only need to find the minimum value of amongst this left max and right max, which means that this tallest bar can actually be used in our help, and we don't even need to calculate this whole left max and right max array by itself. We can actually use a very beautiful concept that is present inside the given array traversal problems, and that is two-pointer solution over here. In the two-pointer function, we are going to have two variables, left and right, initially located at first and last position, and at every single time we are going to check that whatever current element we have, so whatever height at element left or pointer left, and whatever the height at pointer R, we are going to compare these two. So suppose the height at left pointer is actually less than right pointer. What we are going to do is, first we will check that whether the current left pointer we are at, does it contains the left max height, and we are going to initialize the left max variable to 0 at the beginning, and at any point we are going to check that whether we need to update the value of left max. So for left max we are going to check two things. We are only going to check one thing. We are going to check that whether the left max should be the maximum value out of whatever the left max we have stored and whatever the height of left we are at. So this will always make sure that we have the most updated left max value. Once that is done, we only need to use one equation in this scenario, and that equation is left max minus whatever the height we are currently at of pointer L. If this is greater than 0, we can actually add it to our total. So we can just say that total is whatever value we already had for total, plus we can add this whole function to it. And once that is done, we will need to update our left pointer. So on the left side we will move towards the right pointer and we will do left plus plus. And again, suppose at any point we find out a scenario where the height at right is actually, so height at right is actually less than height at left. If that is the case, we are going to repeat the same process. Let me use a different color, but this time we are, rather than doing it for left max, we are actually going to do for the right max. So again, we are going to check for right max that what is the maximum amount we can find. So we are going to take maximum of whatever the right max we already have and whatever the current right height we are at, and once that is done, again we are going to use the same equation, but rather than using left max, we are going to use right max minus whatever the height we are currently at for this R pointer, and if this is greater than 0, we are simply going to add that value to our total variable, whatever we calculate for this one. And once that is done, our right variable is actually going to move towards left side, and we are able to achieve this because there exists some bar that actually divides the array in two portions. Because over here up until this bar, always left max is going to be minimum value, and over here always right max is going to be minimum value. And at any single position, whenever we are at any left and right, we always check their heights, which means that suppose we reach this right before, still in the left side we will have to calculate all of these values before we get here. And once we get to a point where left is actually greater than or equal to right, then we can simply break out of the loop, and whatever value we have stored in the total, we can simply return that. This is a very beautiful approach, and notice that we don't even have to use the full equation over here. We are only comparing any one variable at any point in time, a left max and right max, and every single time we are keeping track of whatever the left maximum or right maximum value that we have been able to find. So if we use this approach, if we use two pointer approach, and if we calculate the time and space complexity, basically the time complexity for this one is actually going to be big O of n. So that is same as it is, because in any case we are going to traverse over the entire input array, but the thing is we are only doing it once, we are not doing it more than that. And if we see the space complexity, actually we are only storing couple of additional parameters like right max, left max, and we are storing two pointers, left pointer and right pointer. So we are not doing any additional data structure, or we are not storing anything else, which means that our space complexity is actually going to be big O of 1 constant time. So this is really amazing solution compared to all the other approaches. This is the most optimal approach. So first of all, we are going to initialize our two variable left and right. Left is going to be 0, right is going to be a height length minus 1. We are also going to initialize a variable total, that is going to be total amount of water that can be stored, and we are going to initialize it to 0. We are also going to have two variables, left max and right max, and left max would be the first element in whatever the height we are given, so height of 0, and right max is going to be the height of last element, so we can say height of right pointer. And now we are going to run our loop. So while left is less than right, first we are going to check for the height difference, and whichever side has the lower height, we are going to work on that side. If left pointer has lesser height, we are going to work on the left side. So we are first of all going to see that do we need to update the left max. We are going to check that whether we are at any valley where we can store some value. So we are going to check that if left max minus whatever the height we are currently at on the left pointer, if that is greater than 0, then we know that we are at a valley and we can store some water over here. So we will update the total amount of rainwater that can be harvested to total plus whatever the height difference we have found over here, which means that left max minus whatever the height we have found over here. And once that is done, we need to update our left pointer to move towards the right side. And if that is not the case, which means that we need to repeat the same process but now on the right side. So first we will try to see if we need to update the value of right max. if we don't need. And now again we are going to check that are we at the valley on the right side where we can store some rainwater. If this is greater than 0, then we can update the total rainwater. And once that is done, we will need to update the right pointer to move towards left direction. Okay, I think that is it. Once this while loop ends, the total variable should have all the entire result, and we can simply return that, and this should give the total amount of rainwater we can harvest. Let's try to run this code. Okay, seems we made some small mistakes. Seems like our solution is working. Let's try to submit the code. And you can see that our solution works pretty fast compared to a lot of other solutions. That is because we are using the most optimal approach. I'm also going to post this solution in the comments. Also, I have created the solution where we need to use two separate arrays to store the left max variable and right max variable at any single position. And you can check it out, that solution as well, from the comments.